I'm about to teach you how to build a tiny violin from this video so you can perform your very own sarcastic melody. We'll cover all the major components including power, software and processing, thermal imaging, and sound. We'll even throw in a bonus feature so you can reprogram the violin to play whatever you want. Here's a small taste of what's possible.
Not.
To make things easier, I've redesigned the original violin to use simpler connections, fewer parts, and most importantly, a guide bonded to the casing. I've tried to make things as easy as possible so that even a total beginner can put one together. And don't worry, I also kept this in mind writing this video guide. It should be an easy to follow, slow-paced walk in the I hope you got all that, because this section's all about how to put everything together. It's going to be a little boring to watch, so to help you stay focused, I'll highlight the tricky bits with my telephone voice to help keep you switched on. To give you an idea of what we're assembling, here's a schematic I prepared earlier. As you can see, there are 6 components to this build, and we'll begin by mounting these 4 first. We'll leave the switch and the sensor for later on. To kick things off, you'll want to arrange the case panels like this. This way you'll keep track of everything and make sure you have all the panels. There should be 6 panels in total. Then we're going to glue in small tiny brackets for the lid. Insert them only into the holes on the longer side pieces. Trust me when I say any hole is not the goal here. In other words, plug holes with the longer wood. Next, attach each component to case panels using hot glue. Follow the guides to pinpoint where each part goes. And if you make a mistake, don't worry, you can use iso alcohol to clean off the glue and try again. Now, this next part is the most hands-on part of this build since it requires a measure of soldering skill. The good news, however, is that once this part is over, it's going to be a cinch for everything that comes after. So heat your hot rod and get ready for some hot, sticky action. We're going to start out by building out our power cables. The positive side supplies power from our Arduino to our thermal sensor and our audio board. So we will need a male-female cable.
Nice.
We're going to first start with a female to female and cut them in half. Then strip them to expose the body underneath. After this, we then twist the exposure together to create an inseparable contact for soldering. Then we're going to cut a length of red single core wire to create the male and complete the male-female power cable. Strip the wire and twist the exposed metal together. I like to use helping hands here as I perform the delicate work of soldering the wires, but as long as the joint is strong, you can do this bit however you want. Finally, finish by sealing the joint with thermoplastic. The next and final thing we need to build is the ground wire. See, that wasn't hard, was it? Now I know this looks like a monstrosity, but it's not actually complicated at all. We'll first start with the switch we left out earlier and solder 2 wires onto the contact points. You need to be careful here because there are 3 contact points and we're only going to be using 2 of them. To figure out which, take a multimeter and set it to continuity mode. In this mode, the multimeter shows 0 volts when the testing points are connected and 0L when not. I prefer using a beeping alert, but it depends on what device you have on hand. Using this tool, we can figure out the contact points are connected by throwing the switch. In our case, we want the switch to connect power when it's turned on, so we set the switch to the on position and test the contact points until we hear our beep. Next, we're once again going to slice a female to female in half and twist them together. And just like before, cut a length of single core black wire and strip the ends to expose the metal. This next part is going to be a bit unusual, so pay attention. We're going to cut and strip ourselves one half of a female to female cable. Choose one that stands out from black here to highlight that this wire is different from the others. I chose blue. Connect this female cable to a 100k resistor. A 100k resistor will have these color stripes on it: brown, black, yellow, followed by a metallic color. Mine is gold, but silver and bronze is possible too. After that, connect the untouched leg of the resistor on the other side to the switch wire. The switch and female cable should not be on the same side of the resistor. I chose the negative dark side of the switch to keep things consistent, but it doesn't really matter which side we choose. Going forward, we will refer to these as Bundle A. Bundle B are the 3 wires we prepared earlier. Get the prepared female-male cuts of wire and twist them together like so. Don't forget to slip on thermal plastic as you go. Now finally, with Bundle A and B, join the end that leads to the switch on Bundle A to Bundle B, where the 2 females and male meet. And once again, cover the exposed metal with a thermoplastic sleeve. And that's it, the hardest part of the build done.
Congratulations, Reg, it's a squid.
With the hard stuff done, all that's left is to plug everything together. We'll first start out with our squid wire, bring back the panels with the components on them and rearrange them like so. Finally, after holding off for so long, we can reunite the switch into its proper place. Insert it from the outside wires first. It should be a snug fit. Next, connect the Arduino board with the male wire we prepared earlier by inserting it into the header labeled ground. After that, connect the squid wire to the sensor using one of the female connections. We kept from gluing the sensor with all the other components because the header pins are on the other side of the labeling. Remember, the pin order reverses itself when you flip it over, so keep it unglued for now and use the labels. There'll be a pin marked G and D for ground, connected to that. On the audio board next to the switch, there'll be another ground pin. Connect the remaining female wire to this pin. Remember the special wire we connected to this resistor? Mine was blue, so I hope you managed to find yours. This wire connects to the pin marked gain on the audio board we were looking at. This wire sets the volume level on the board. Finally, the other remaining loose wire on the switch, mine is red, connects to the header labeled 0. We should have all ends of the squid wire joined up now. Next, we'll hook up the positive power with our red male-female cable.
Nice.
First, we'll take the male end and plug the header on the Arduino marked 5 volts. This header will supply power to every other component. Next, locate the pin on the audio board marked VN, which stands for voltage in, and plug in one of the female connections. Then finally, on the thermal sensor, locate the VN pin and connect the remaining loose end. With the positive and ground connected, our build is powered. Awesome, isn't it? Like the ending to ground pool in voltage in. Don't worry, our build only explodes after the battery is connected. This next part is just going to be just like before, just minus the splicing of wires, which is my long-winded way of saying easier. We'll begin by peeling ourselves a pair of male to female cables. Mine are Australian green and yellow. These wires are to connect to the serial clock and serial data on our thermal sensor. These are usually printed short form on pins as SCL and SDA. Locate these labels on both the thermal sensor and the Arduino and connect them together with our male to female cable. Next, we'll connect the left and right clock, the bit clock, and the data in pins for the audio board. These are labeled LRC, BCLK, and DIN respectively. The pins we're connecting to on the Arduino will have different labels to these, so pay attention. Connect the LRC to pin 3, BCLK to pin 2, and DIN to pin A6. I tried to keep these as close as possible, but there were technical reasons why A6 is off by itself. Next, we'll hook up the speaker. The speaker has a positive red wire and negative black wire. These are connected to the big green terminal on the audio board. Be sure to screw in the red to the positive side and the black to the negative side. If you reach this point in the video, job well done, because everything is built and all that's left is to flash the software. To do this, you need the Arduino editor, so head over to the official website to download the installer and download the tiny Violin files from my repository in GitHub. The links are in the description. Once you've unzipped the tiny Violin folder, open the tinyviolin.ini file with the editor. Connect the Arduino to your computer using a USB cable and set the drop-down menu to MKR0. If you can't find the option for the MKR0, you can click this icon on the left and search for it. You should find an entry titled Arduino SAMD boards and install that entry, and you'll have the Arduino MKR0 available. Finally, click the arrow and wait for the loading bar to complete in the output. The last thing left to do is copying the Woe Is Me WAV file we downloaded earlier onto our SD card and insert it into the Arduino. Now, for the moment of truth. If you've done everything correctly, you should be able to do this. I know what you're thinking.
Nano machine, son!
But for the rest of you, you might be wondering why this doesn't sound like a violin. And that's the beauty of this build, because you can basically reprogram it to play whatever you want, and I'm going to show you how. First, let's take a look at the code. Right at the top here, you can change these lines to change the volume or target different WAV files you load onto the SD card. Just make sure that whatever you type between these two quotation marks matches the file name on the SD card. The only catch is this build only accepts a very particular format for the WAV files, so I'll also walk you through the conversion process. You'll need to download Audacity for this, so download it from the official website and open the music file you wish to convert. Click File, then Export Audio, then change the format to WAV. Click Stereo here, set the sample rate to 44,100 Hz, and change the encoding to signed 16-bit PCM. Then export. And that's it. This file is ready to copy into the SD card. You might have noticed this extra folder in the zip. This code is similar to the Violin code, but I had to change it slightly to play shorter audio clips. So just like the title suggests, you'll want to upload this code instead if you want the nut button feature. Just follow the previous steps from uploading the code with the editor to loading a converted WAV file on the SD card. The process is exactly the same. With our build detecting movement and sounding great, all that's left is to glue everything together. Begin by finally gluing in the thermal sensor, now that we've tested everything works, and connect the battery. I lied, it won't explode. Unless it's from a Cybertruck. I've done some reading on the net and seems like there's a small flaw with these batteries sometimes and the wires are around the wrong way. If you switch them by stripping them down and connecting them the right way by swapping the wires, it should work as intended. I'll fix mine later, but you can fix yours now if you want to. With all the components glued in, we can now glue and fold the box together. Coat the edges where the pieces touch and assemble the box. Start with the sides first, forming a ring before pressing down into the bottom sensor plate. Take extra care here not to unplug or tangle any wires as you do this. Lastly, fit the lid with a few M1.7 screws. Whew, and that's it. Well done. You now have the technology. You now have the capability to build your first violin. Consider subscribing and let me know what you end up programming your violin into. I'm excited to see the results. See you in the next one.